Okay guys, welcome back. So in the last videos we talked about the gas laws and the other concepts, and also some concepts and equations of the KTG, which is the kinetic theory or the kinetic molecular theory of gases. So that was about the basic gas laws. So in this video also I'll be talking about a simple law, right? It's actually based upon the ideal gas equation or the ideal gas law that I described a few videos back. So if you have not watched that video and if you are not well versed with the ideal gas equation and its concepts and its applications, I invite you to watch that video and come back, because it will be somewhat easy for you if you follow that and come back. Alright, so what I'm going to talk here is the relationship of pressures, right? So my topic here is the Dalton's law of partial pressures. So before explaining what is meant by a partial pressure, I will derive the equation for Dalton's law of partial pressures and then go to the concept of partial pressure, because partial pressure is I have seen that many students, right, many of my viewers and many of my students and many of my question papers. So you can find my question papers in SlideShare and other phase. Even in I have created a Facebook page at the WSing presentations. So many of my viewers have noticed that the partial pressure and the partial of other things, distillation and the partial pressures of gases and the molar fractions, so are somewhat to be complicating. So due to these reasons, I will start it from the normal configuration or the normal definition of Dalton's partial pressures, and then I will derive the equation for Dalton's law of partial pressures, and then introduce you as to what a partial pressure is and what a partial pressure can do in terms of gas laws. Alright, so my video is my video's intention is to derive an equation for Dalton's law of partial pressures. Alright. So I'll take three systems like this. Three systems. Like this. I'll take this to be completely of neon, this to be of argon, and this to be of xenon. Now I'm saying this due to a reason, right? Now I can take any gas, hydrogen, helium or any gas, but I'm taking this neon, argon and xenon due to reason. This reason is that now according to Dalton's law of partial pressures, now these three gases or two or more gases that I'm using for this equation and for the concept of this equation shouldn't be mixing with each other, right? Should be mixing with each other. Now for example, there are some gases that they react together and form new components. So if they form new components, if it is a solid and liquid, it's no problem, but if they form new gaseous components, right, new gaseous components, what actually happens is that we have to take the partial pressures of the products as well. So for the complex, to remove that complexity, for the simplicity, the Dalton's law of partial pressures expresses that the gases that are used in this combination or gases that are used in this mixing shouldn't be reacting with each other. So I took three rare gases, neon, argon and xenon, due to that reason. Now in order to apply Dalton's law of partial pressures, we have to make the volume and the absolute temperature constraint. So the volume and the absolute temperature should be constraints. So this is very similar to this derivation is very similar to that of the derivations that I described in the concepts of Boyle's law and Charles' law, and even in the combined gas law. But what actually happens, as in the ideal gas law equation, we have to take some moles of this gas, and this gas, and we have to derive the equation. So the molar value is an important concept here. So you can't ignore the number of moles that have been used by these individual gases. So I'll take the number of moles of neon to be N1, number of moles of argon to be N2, and number of moles of xenon to be N3, and the pressure exerted by neon to be P1, pressure exerted by argon to be P2, and that of xenon to be P3. So you know that if you were given some value for the number of moles that have been used in this gas setup, you have to apply ideal gas equation, because all gas equations are based upon mass constants theory. So since the number of moles is differentiated, or the number of moles is different from system to system, you cannot ignore the number of moles and you cannot apply other gas laws. The only gas law that you can apply here is the ideal gas law. So I'll apply ideal gas law to each of these gas samples, and I'll take the volume and temperature to be a constant, and I'll take those to be V and T. So for the neon sample I can write, so PV equals nRT, so I'll directly write the equation that I have been used here. So PV, if PV is equal to nRT, so P here is P1 and V is taken as V, equals N is N1 times R times T, right? So I'll explain what happens here. So what I'll do here is that I will isolate N1 here. N1 equals, I'll explain as to why I isolated here. So N1 equals, you can divide both sides by RT, because T is not equal to 0, because T is an absolute temperature, right? Absolute temperature is 0 is just a concept, but it's not practical. So T cannot be 0 for any gas sample, and R is not 0 because R is a universal gas constant, right? It's not 0, so RT is not 0, you can divide it by RT. So if you divide RT by this side, you will cancel RT to RT, and this side it will be P11V by RT. Now this is N1 equals P1V by RT. This is for the neon sample. For the next samples, argon and xenon, I will not write this equation, I will just substitute the values in place of this equation. So for the argon sample, we can say that here N1 equals P1V divided by RT. So for the argon sample, you can say N2 equals P2V by RT. And for the xenon sample, you can say N3 equals P3V by RT. Alright. Now these are for the individual gas samples. Now consider a sample in which all these gases are mixed together. Take a simple sample like this. Now in this sample, N1 moles of neon are mixed together with N2 moles of argon and N3 moles of xenon, right? So N3 moles of xenon. So that the total number of moles in this sample is N1 plus N2 plus N3, right? Now if you put PV equals nRT for the whole sample, what you will get if you substitute the value of N here and P here, so that the total pressure is P and the total number of moles is N, what you will get here for the whole sample, N equals P times V divided by R times T. Now what I am going to do here is I just can substitute this here, right? So that is the reason as to why I isolated N1, N2 and N3. If I could form a relationship like this, if I could form an equation like this, what I am going to do is I am going to just substitute the values and then take another equation. Right. Now you can say that the total pressure is the addition of the pressures, because although they don't react with each other, the total pressure is not the addition, right? So we have to derive that, right? The total pressure is the addition of P1 plus P2 plus P3, but that's true. But what actually happens is that we have to derive that. Alright. So N equals PV by RT. So I can substitute that here. So this is PV by RT. So this is N1 is P1V divided by RT. N2 is P2V divided by RT. And N3 is P3V divided by RT. So I can say P times V by RT is equal to, I can take V by RT out of all those things, so that this is P1 plus P2 plus P3 times V by RT. So V by RT is not equal to 0 because the volume cannot be 0, as well as I mentioned a little while ago, RT cannot be 0. So V by RT is not 0, so you can cancel it. So P is equal to P1 plus P2 plus P3. Right? So the total pressure of the system is the summation of the individual pressure. So this is not only limited to 3 gases, it is limited to n number of gases, to 2 gases, 3 gases, 4 gases, 5 or 10 or 1000 million or n number of gases. So this is a very important relationship in gas laws that has been derived in the gas laws, like that of Charles law and Boyle's law. This is of utmost importance because there are systems in which there are more than 2 or 3 gases that have been mixed with each other. So if the volume and the temperature stays constant, you can simply say that from Dalton's law of partial pressures, that the total pressure of the system is the summation of the individual pressures. So what is meant by this? So what is meant by P1, P2 and P3 is the concept of partial pressures. Alright. So what is a partial pressure? Now you know that P equals P1 plus P2 plus P3. Right? You know P equals P1 plus P2 plus P3. Now what is P1? So you know that N equals PV divided by RT, right? And N1 equals P1V divided by RT. If I take this to be equation number 1, and if I take this to be equation number 2, right? Equation number 2, what happens when 2 is divided by 1? When 2 is divided by 1, what actually happens is that N1 divided by N, right? So the left hand side will be N1 divided by N will be equal to P1V by RT whole thing divided by PV by RT, right? Whole thing divided by PV by RT. So what actually happens is V by RT will again cancel here. V by RT will again cancel here. So N1 by N will be equal to P1 by P. Right? So you know that N1 by N. So you know that N is equal to N1 plus N2 plus N3. So that you know from chemistry, right? If you have used it chemistry and other concepts, you know that the mole, right? Some moles of a gas divided by the total number of moles for the whole gas is the molar fraction of this gas. So this is the molar fraction, which is normally denoted as X. The molar fraction is the molar fraction. Molar fraction is equal to P1 by P. So P1 is the partial pressure due to the gas 1, P is the total pressure. So this is we'll call Px is the pressure fraction. I'll call it pressure fraction. And also, since x equals P1 by P, you can also say, since x equals P1 by P, we can say P1 is equal to x times P. P1 equals x times P, so that the partial pressure of any gas is the molar fraction of that gas times the total pressure. The molar fraction of the gas being the number of moles of that gas, number of moles that the gas is contributing towards the whole sample, divided by the whole number of moles. Whole number of moles means the total number of moles as contributed by all the gases times the total pressure. So you will get the partial pressure. So that is the concept of partial pressure. So this is called the partial pressure, and P is called the total pressure, and X is the molar fraction. So for any gas in which the volume for a combination of gases in which the volume and the temperature stays constant, the partial pressure by a gas, or the pressure that is exerted by a gas, is the product of the molar fraction of that gas times the total pressure. Alright, so that is the importance of Dalton's law of partial pressures. So Dalton's law of partial pressures is not only limited to gas laws. Dalton's law of partial pressures also goes into the lengths and breadths of diffusion. Diffusion means in the concepts of distillation and the other concepts. In the distillation and the partial distillation and the other concepts. So it's of utmost importance. I think even it's more than important than the Boyle's law and Charles' law, because it's used in many concepts in chemistry, right? Dalton's law of partial pressures and the concept of partial pressure. Alright, so this video I talked about Dalton's law of partial pressures. In the next video I'll be talking about another concept of gas laws, which is thermodynamics. See you then.